And we are now recording. The slideshow will start from current slide. And the only other thing I know about, and I think probably everybody else knows about it too, sort of a sad news situation. There's no classes next week. Yeah. Y'all get the entire week off for Thanksgiving. And we have to go to meetings Monday, Tuesday, and have a duty day on Wednesday, but everybody's off Thursday and Friday. Which means, of course, the college is still open Monday, Tuesday, and Wednesday. So if you have business to do at the college, there will be someone here to take care of it. With this caveat, I would say try to get it taken care of Monday or Tuesday or no later than Wednesday morning, because Wednesday afternoon things get pretty sparse around here, day before the holiday, that kind of stuff. And in fact, usually a vice president will call sometime, or someone will call sometime afternoon on Wednesday and say, y'all can go home. So after that point, catching anybody here is going to be hard fun. So if you have business to do with the college, try to get it done Monday, Tuesday, or no later than Wednesday morning. And we doubled our class size. Excellent. Patrick is here. Okay. Didn't know you were that important, did you? You are. Okay. Well, let's see. Howdy. And here is increase our class size by 33%. Okay, Siegfried's here. So the bottom part of the alphabet is doing fairly well. It's better than the top part anyway. All right. Now my memory has it that we ended the last class talking about the temperature scales. Okay, I think we got all that covered. The conversion formulas for Celsius to Fahrenheit, Fahrenheit to Celsius, and Celsius to Kelvin. And we did a couple of examples with those, 4.1, 4.2, and 4.3. So any questions on any of that? Okay. Then we're starting today in the new text on page 92, whatever book you got somewhere close by. It's on the topic of heat. This is section 4.3. And there's a closer look we're going to talk about just a little bit and then move into that. But I did remember this. I wanted to say this. Let's just talk a little bit about what we're doing from now on. Okay? We've got today, we're 3:15 to 5:15 is class. We'll stop at 5:15 and have our lab, which is 5:15 to 7:15. And then at the end of the lab, we'll have the test on chapter 3, which was energy. Okay? And I hope you have your formula equation sheets ready for that. Okay? And they keep a coming. Increase class size by 25%. Okay. Now you're in here somewhere. Yes. Tiffany is here. And Philip is here. All right. Keep on coming. Okay. We're up to 1, 2, 3, 4, 5. Yeah, that's all we got so far. I thought it was 6. Only 5. Okay. So today is continuing chapter 4. Go until 5:15. We have the first lab in chapter 4. That will be from 5:15 to 7:15. And then when we finish that lab, if it's before 7:15, we will you'll have the test on chapter 3. If we don't finish all the write-up of the lab, you have time to do all the calculations all the data gathering in the lab. It's a pretty short lab. I don't think it'll take too long. Okay, so hopefully we will be able to start the test early and leave early. So then, what does that leave for Thursday? Thursday we'll continue in chapter 4 and have the second lab in chapter 4. And that will be just 2.5 hours of class and 2 hours of lab. it just depends on whether we finish the chapter on Thursday or not. I doubt if we will, but if we do, then we'll have the test. This is sort of sad, but y'all realize, don't you, it's sort of bad news. I told Heidi there's no class next week. Oh, shucks. Get over it.
Don't you hurt my feelings.
Yeah, okay. And Emmanuel's here. You have the whole week of Thanksgiving off. We have just Thursday and Friday. We may get part of a day on Wednesday, but we have meetings Monday and Tuesday, and then I think a duty day on Wednesday. Okay. All right. So that means test 4 will be coming up the Tuesday after Thanksgiving break. So you have plenty of time to study it, won't you? Yes. Okay. All right. Anything else before we get going today? That's all I know about. No new announcements. What's that?
I said test 4 Tuesday after Thanksgiving.
That's what it looks like it's going to be now. I think we'll finish the chapter not today, but Thursday. So we should be ready. And we'll have a lab before it, and then the test. I think we'll have a lab before it. This may be the chapter with only 2 labs. I have to check that. But we may be far enough in chapter 6. We're going to skip chapter 5. In chapter 6 to have the first lab is up. Okay. Now, then after Thanksgiving, I can't remember, 1 week of class or 2? 2 weeks.
2 weeks.
Now, that include finals? I think so. I think so. We'll have, I think it's 3 days of class after Thanksgiving. We'll have class the Tuesday, Thursday, and the following Tuesday, and then Thursday have the test. I think that's how it goes, but we'll see. We'll check on that and see. All right, so we are getting close to the short rows now. Okay, so let's continue. In chapter 4, we finished the part about temperature and temperature scales and conversions and things like that. Today we're starting on heat. Before we get to heat, this room's a good room to talk about heat, isn't it? But actually, it doesn't feel as cold today as it has others. I think because it's cooler outside, this doesn't blowing as hard. So that doesn't make a lot of sense, but I think it must be the case because usually it's blowing down on me fiercely. There's a closer look here at goosebumps. I've heard it called goose flesh and other things like that, and shivering, and what in the world is happening with that kind of stuff. And so it's well worth a read. I think you'll probably learn stuff. I know when I read it the first time, I've found out stuff I hadn't known before. Interesting stuff. So let's move on to heat. Now, this is, heat is an unusual concept, okay? Quite often we use the term thermal energy, and I will use that almost interchangeably with heat, but it's not quite the same thing. Heat is a form of energy transfer, not the energy itself, but energy transfer between 2 objects. That's what heat is, okay? This room doesn't contain a certain amount of heat, okay? It has a certain amount of thermal energy, but if some of this heat is escaping to the outside, that's an energy transfer, that's heat. Or to out in the hallway, or heat coming in from outside, not today probably, but other days it could have been earlier in the term. That's what heat is, a form of energy transfer between 2 objects. And the energy being transferred is thermal energy, not just any old energy. Now, heat is also external energy. Now remember, we've talked about this before. We have the macroscopic view of things and the microscopic view. And this chapter probably does more of that than any other. All of them do it a little bit, but this one probably more than most. The external energy is the total potential and kinetic energy of an everyday sized object. Macroscopic. Okay? Now this is what do we usually call the total potential and kinetic energy. We have a name for that, the last lab. Sum of the potential and kinetic energy. Y'all are auto? Okay. Mechanical energy. Mechanical energy. Okay? That's what we usually refer to as the external energy. Now that may be converted to or even from heat. Okay? A transfer there. But you also have the internal energy, the total kinetic energy of the molecules in that object. That's the microscopic scale, okay? And that's related to temperature, okay? Because the temperature is related to the average kinetic energy of the molecules. Now, external energy can be transferred to internal, and I think it also goes the other way, but if it is, that results in a temperature increase. Okay? My hands here, if I rub them together, that's an external energy, mechanical energy, kinetic energy. But after a while, I can feel it. My hands are warming up. That's a change of temperature, and that's somewhat internal, somewhat external, and that results in the temperature increase. Okay? So external energy can be transferred to internal, resulting in a temperature increase. Here's a gal pushing the desk across the, or table across the floor. Now, that's external energy. Her pushes against the table. As she's pushing, I bet you can hear vibration on the floor. I don't want to move the desk there. Well, no, that's all right. The projector isn't associated with the desk. Okay? You heard that when I did it. Okay? That means there was vibrational energy that created sound. Okay? And some of that, if you had a very sensitive thermocouple down on the floor, you would have seen a little bit of energy, temperature increase. If it was very sensitive. Okay? So the internal energy is the increased vibrations that come with the friction of the table legs with the floor. Okay? So external energy increased the internal energy, which could have, and probably did, very slightly increase the temperature of that interface down there. Of course, that was dissipated very quickly because it was a very small change. All right, now, there is another figure in the book besides the one we just saw, and this shows how friction results from in increased temperatures. Molecules on one moving surface will catch on another surface, stretching the molecular forces that are holding them. They are pulled back to their home position with a snap, resulting in a gain in vibrational kinetic energy, and that will, it's not going to be a lot, but that could have a little bit of an internal energy increase, which leads to temperature change. And that's what's happening rubbing your hands together. Because you see your hands are rough, mine are anyway, the handprint, fingerprint type stuff there, they're rubbing against each other, that increases. If I push harder, I can feel it gets hotter. If I don't push as hot, it almost stays the ambient temperature, just increases a little bit. Okay, that figure was there. Now we're on heat versus, or heat as energy transfer. The title of this is Heat versus Temperature. Kind of the same thing. Remember what temperature is? A measure of the hotness or coldness of an object based on the average molecular kinetic energy. How fast are those molecules moving on average within that material? Okay? Now what's heat? not a measure of hotness or coldness, not based on average molecular kinetic energy. Heat is based on the total internal energy of the molecules. That's not just kinetic, that's also potential as well. All right. Here is Amika. All right, good deal. Bottom part of the alphabet, doing quite nicely. Little Tiffany's the only one holding up the top part of the alphabet. Okay. All by yourself. You got that whole weight on your shoulders. Okay? So heat is based on total internal energy of the molecules, which includes kinetic, but also potential energy of those molecules. Now, here's an example of why heat and temperature are not the same. Okay? What if we have a full liter, the mellow yellow there, is that a liter? That's probably a little less than a liter, isn't it? That's a little less than 2. Mellow yellow, is that, Philip, is that a full liter or is that a little less?
That's 16 ounces.
16 ounces?
Yes, 20 ounces.
20 ounce, which is how many liters? Does it say?
591 milliliters.
Okay, so that's about half of a liter, a little bit, about 3/5 of a liter. Okay, about 3/5 of a liter. So a liter is a little bit bigger than that. Big old mug, that would be 1 liter of water at 90 degrees Celsius, which is pretty hot. Because 100 degrees Celsius is boiling, so this is hot. Okay. Now, I also have a little cup over here, which is about half that bottle there. This would be 250 milliliters, a quarter of a liter of water at 90 degrees Celsius. The temperature is the same for those 2 cups, right? Which one of those would melt ice, more ice?
Which one would melt more ice?
Yeah. This one for sure, because it takes 4 times as much ice to cool this as it does that. Why? Because the volume's different. There is more heat in this cup than there is there, even though the temperatures are the same. So heat and temperature are not the same thing, okay? I like to say a bathtub full of hot water as opposed to a thimble full of hot water. Even if this was hotter water, bathtub may be at 80 degrees, the thimble could be at 90 degrees, but the bathtub can take a lot more heat than the thimble, okay? So heat versus temperature. Now, continue with heat, and this is now heat defined is the title of the subtopic here. What is the definition of heat? They've only given it to us like 2 or 3 times now. A measure of the internal energy
That has to be
absorbed or transferred from another object. Because heat is not how much heat there is, it's how much is being exchanged. Heat is the exchange of energy, and that's a measure of the total internal energy that has either been absorbed or transferred from another object. Okay? Now there's 2 related processes. Heating is increasing the internal energy of an object, whereas cooling is decreasing the internal energy of the object. Okay? Internal combustion engines, heating. Compressing a gas, heating. Cooling, expanding a gas, or other type things like that would be cooling. So, what are some of our heating methods? Okay? One dead giveaway that you have heating going on is when you see a temperature difference. You cannot change the temperature without changing heat. Okay? That is a dead giveaway. Energy always moves across. And where does energy move from? As every other type of energy, from a higher potential to a lower potential. So with heat, that would be from a higher temperature to regions of lower temperature. Now I can remember my dad saying, close the door, you're letting the heat in. No, you're letting the cold out. Okay? No, you're not letting the cold out, you're letting heat in. Because heat always moves from higher temperature to lower temperature. Now, in the wintertime, close the door, you're letting the heat out. That was a very good statement because the heat is always moving from warmer temperatures to colder temperatures. High temperature to cold. But when it's summertime, close the door. The best statement would be you're letting the heat in. You're not letting the cool out. Though it's the same result, but it always moves, energy always moves from a high potential to a low potential. Unless you force it. And y'all do that all the time. You know what air conditioning is, heat pumps, you're forcing it one way or another. Okay? Now, there's another thing about a heating method. Sometimes you have energy form conversion. Not the temperature conversion, but energy form conversion. Okay? And that could be like from doing work. Rubbing your hands together. You're doing work and you're creating heat. So you're going from kinetic energy to heat energy. Transfer of heat by doing work. Okay? We'll also look at some other heat methods, and it's kind of an energy form conversion, but we'll tackle that later. Okay? Stand by, that's coming up. How do we measure heat? Now we're talking about page 94, or somewhere thereabout if you're in a different book. And like I said, heat is an unusual kind of substance. It's not specifically an energy, it's an energy transfer. Okay? Back in the old days, heat was considered to be not a form of energy, but an intrinsic material that lived within a body. Okay? Now that sounds strange to us, but it really wasn't. That was sort of normal seeming. If you think about it, and boy, wasn't it just a week ago those leaves were green? Yes. That I pointed them out, and now I hardly see any green at all. I mean, they've changed color in a week. In fact, I'd say less than a week. I think Thursday they were mostly green with a little bit of color. Now they're almost totally colorful. Okay. Off the point, but if you think about, that's why I looked out the window. And this is not science, this is observation. Okay, but think about this. The tree out there in the middle of summertime, okay? Obviously it's hot out there, right? But you go and sit under the tree and it feels a little cooler, right? You're in the shade. So the idea was whatever heat was, it was something the tree was capturing, okay? Okay. Now, that's not exactly true, but it's not far. Then what happened? When the tree captured it, and the tree grew, and you got wood, and then you take the wood, cut the wood, and take it into the house and put it in the fireplace or the cook stove. And then you release that heat. So they thought of heat as being an intrinsic material. Now, they never could determine any mass for it, but they thought it was one of the elements. In fact, back in Aristotle's day, we've talked about him before, he said there were 4 basic elements. That's all, folks, 4. And guess what he said they were? Earth, second, earth, wind, water, and fire. Guess what fire is? Heat, exactly. He thought it was a basic element. Now, 3 of those made a singing group back in my day, but y'all don't remember that, do you? Earth, wind, and fire. Good deal. Okay. Just didn't have any water in it. Okay. So, all right. They didn't drink water. Never mind. I won't go there. Okay. So, later, much later, I would say the 1700s or so later, Aristotle was BC. I mean, he was way back. Okay, probably 2,400 years ago, But then as much as 1700s or so, when they came out with the first real list of elements, a guy named Lavoisier, a French guy, chemist, We won't get to him even in the chemistry chapter, but he was a famous chemist. He started compiling a list of what he thought were the known elements. He had a few wrong, but he had a lot of them right, like copper and iron and oxygen and hydrogen, and he had a lot of them right. I'm guessing he had probably in the 30s or 40s. But in the list, he had a few compounds. I think one of them was lime, which is calcium carbonate, not an element, okay? But he had a few in there that were wrong that way. But he had this one element he called caloric, which was basically the old Aristotelian view that heat was an element, that energy was an element, okay? Heat, fire, okay? They still had that as listed as an element. We know today heat is not an element. It's not a massless quantity. It is a form of energy transfer. So how do we measure this? Well, we had several units of measure. The original heat they measured, like we called, Lavoisier called that element caloric. That was from the, I'm sure this is Latin or Greek or something, calorie, okay? That is a metric unit of heat. It's not the SI unit. It's the metric, one of the metric units of heat. Now, here's the definition for it. What is the standard substance that they use for most building blocks, okay? What substance do they use to measure the standard amounts with? We've hit it in a couple places so far. You might not remember it. What's the most common material on the surface of the planet? Material on the surface of the planet, most common. Water, exactly, water, okay? And water is everywhere. It's a very stable thing, everything else. So what they said, calorie was the energy needed to raise the temperature of 1 gram of water. 1 gram. Now 1 gram is a very small amount of water, okay? It's a gram of water would be across your little fingernail, that's about 1 centimeter, approximately. So 1 centimeter wide, 1 centimeter deep, and 1 centimeter high. That's a cubic centimeter. It would be one of those tiny little cubes of sugar that hardly sweetens anything, right? Tiny little thing. About an aspirin tablet or 2 size, something like that. 1 gram of water, 1 degree Celsius. That's what a calorie is, a very small amount of heat, okay? The energy needed to raise the temperature of 1 gram of water, 1 degree Celsius, okay? Well, that was so small of a heat measurement that they started using kilocalories, which would be how many calories? Kilo means? Kilo. Yeah, 1,000, 10 to the third, okay? 1,000. So a kilocalorie is a K-C-A-L, kilocalorie. C-A-L is abbreviation of calorie. Now that's a substantial amount of heat. That's the energy needed to raise the temperature of 1 kilogram of water. Now a kilogram of water would be approximately this book's mass of water, okay? That's about a kilogram. Maybe not quite, but close to it, okay? That much water to raise that 1 degree Celsius, that's a fair amount of heat, okay? If you think of a pot with that much water in it, it's going to take a fair amount of heat to raise it 1 degree Celsius, okay? Now, I don't know if you've noticed here, little c for this calorie, kilocalorie, then they put calorie again. And what's the difference between this calorie and that calorie?
That must be a person's name.
No, it's a capital C. No, it's the Greek or Latin word that meant heat, okay? So, but notice, capital C calorie is 1 kilocalorie, and the abbreviation for it is capital CAL, or this is little CAL. See, the food scientists and things like this, they were tired of measuring heat in little c calories. They were using kilocalories, and they said, well, this kilocalorie, that's 2 extra syllables. Let's just call it calories. So capital C calorie is really 1 kilocalorie. Notice on your bottle or can of soda or drink or whatever, and see what the calorie content is. 90, and was a capital C or a little c? Capital C. Those are kilocalories. Okay? Kilocalories, okay? So that's what they use to measure. When you see how many calories is this, it's not those, it's these. 1,000 of those, okay? So this is a very small amount of heat. That's a much bigger. Now, in the English system, British system, they used a British thermal unit as their unit for heat. A BTU. Y'all have heard that before, haven't you? Air conditioning, okay? BTUs. They're getting away from this now, but it's still pretty common, okay? That's the energy needed to raise the temperature. And remember, we don't use mass in the British system. What do we use instead? Weight, pounds. We weigh 1 pound of water, 1 degree Fahrenheit, because in the English system they still use the Fahrenheit. Mostly because the French use the, Celsius, okay? British and French don't usually want to do the same thing, ever. Okay, now, which is bigger than a BTU or a little C calorie?
Pound.
Yes, a pound of water is a whole lot more than a gram of water. A gram of water is that little amount. A pound of water, this book is a little bit more than a pound. So that's a lot more water. Now, on the other hand, 1 degree Celsius, is that bigger or smaller than 1 degree Fahrenheit? A degree Celsius versus a degree Fahrenheit. Which is bigger, which is smaller? Second? A Fahrenheit degree is close to half, a little bit more than half of what a Celsius degree is. Okay? Because remember, there's 100 degrees between freezing point and melting point of water. That's the same thing. Freezing point and boiling point of water in the Celsius scale, but there's 180 degrees difference in the Fahrenheit scale. So 1 degree Fahrenheit is a little more than half of a degree Celsius. But a pound is a whole lot more, tons times more, not that many, than a little C calorie. So there are some other conversions we'll get to, but here's one more on this slide. What's the mechanical equivalence of heat? Now remember, they used to think heat was an element, a substance and stuff. They had no clue it had anything to do with energy. Okay? Anything to do with energy. Along came a guy named William Thomson. Now we had did I say his name right? Here's James. Okay. Tiffany, you got some help on the front part of the alphabet, bringing it up. Only 2 of you in the top half, the rest of them in the bottom half. Okay. Let me see, have I got his name right? Goodness, I'm going blank on his name. I think he's at the end of the chapter. Let me see. William Thomson was Lord Kelvin, I think. This is a different one. Benjamin Thomson. Okay. Yeah. William Thomson, Thomson, that was Lord Kelvin. Benjamin Thomson, with a P in it, he actually had a title too. Count Rumford. Okay. Now, was he born with that, you reckon?
No.
Not really. Here's what he was. Not very popular, maybe for loyal Americans. But back around the late 1700s, what was happening in this country? Second? The War of Independence. We were fighting against Britain to become independent. We were colonies. We wanted to become our own nation. And it happened. Okay? However, Benjamin Thomson was an American at that time, except we weren't quite Americans yet because we were still British citizens. And he said, you know, I want to stay a British citizen. I don't want to rebel. So I think he may actually have been friends with that really infamous character. Goodness, I'm going to blank on his name. I keep thinking Aaron Burr, but that's not it. It's he was hung for treason. Goodness, what is his name? Benedict Arnold. Remember him? He was a traitor. Guess what? Benjamin Thompson was a friend of his, I think. And he was a traitor to our cause. He counted us as traitors to England because he counted himself English. So when the war was beginning to happen, maybe even after it started happening, rather than join the colonies, he was against the colonies, and I think he went back to England. And because he gave up that, and he was an engineer, quite a good engineer, good scientist, and because he came back, they gave him his honorary title of Count. So he was Count Rumford. That's the name I was remembering. I couldn't remember Benjamin Thompson, but Count Rumford. Okay? Now, he was working actually in Europe at the time, even though he was a British citizen. He was working, I think, for the Germans or Prussians or somebody, whatever they were calling themselves back then. They were carrying on the fight against somebody, so they needed some armaments, okay, as in cannon. And how they made cannon back in those days was they poured the mold of the cannon, the shape of the cannon, the barrel of the cannon. They poured it solid with probably cast iron. I don't know for sure. I'm guessing it was cast iron. And then they turned around and drilled out the bore because it was sort of hard to, have something in there and just pour around it, So they poured the entire thing and then drilled out the center. And he noticed in the process of doing that, he was an engineer, he's in charge of doing that. He noticed that, of course, the bits that they used to drill those things out got dull really fast. And he noticed that he could tell when a bit was getting dull because it wasn't drilling as well, but also producing a lot of heat. Now, time out. Remember, they thought heat was an intrinsic property of the material. So they thought wood contains a certain amount of heat. Certainly iron must contain heat because you heat it up and it melts and stuff like this. So they thought iron contained a lot of heat. But Rumford, being a good scientist and a good engineer, said, wait a minute here. If that heat is an intrinsic property of the material, then it only should have so much in it, right? So here's what he did. I think he was doing this probably down around Munich. I'm not sure, but Munich is close enough to the Alps that the water coming into Munich was pretty cold, especially in the springtime because it was coming out of snowmelt from the Alps, the mountain range. So he decided to try something. Now, they had poor old horses that pulled the thing and went around in circles, and as that horse went in circle, it turned the bit, and the bit is what ground out the metal in the thing. We had an old barrel that was faulty, okay? He wasn't going to use it anymore. Maybe the hole was off center or the metal cracked or something happened. He also had an old bit that was about as dull as my razor blade. It was dull, okay? So he said, let me try something. And he had the poor old horse turning this dull bit into this old cannon, which he had already, it was trash. He filled that with the coldest water coming off the glaciers, off the snowmelt that he could. Almost ice cold water. Put it in there, started turning the bit, the dull bit. Within an hour, he had that water boiling. And he found out he could keep it boiling just by keeping that horse walking in circles and stuff. He said this heat is not an intrinsic property of the metal. The heat is coming from the work that the horse is doing, turning that dull bit against that old metal. So it's not an intrinsic property. He was the first one to see that there was an equivalence between work and other types of energy and heat. And he didn't come up with this number, but the guy we talked about last chapter did. James Prescott Joule. He was a careful measurer and studier and experimenter, and he was able to determine that it took 4.184 joules, which is a small amount of heat, to make 1 little C calorie. So a calorie is actually bigger than a joule. And you thought joules were, if you thought that was a reasonable size of energy, no, it's not. That's a very small amount of energy. It takes a little over 4 of them to make 1 calorie, and then 1,000 calories to make 1 big C calorie, or kilocalorie. And the BTU is in between those. It's in between a little C calorie and a big C calorie. In fact, in your book, I think you can find that conversion, and it's worth looking at. Well, I thought it was here. Man, okay. It used to be in the text, and I don't see it in here anymore. Okay? That's bad. That's a pretty important conversion. If you go to the front inside cover, if you have one of these, and look under energy, you see the 1 calorie is equal to 4.184 joules. 1 joule is equal to 0.738 foot-pounds, or 0.239 calories. And there's foot-pounds to joules, and there it is. 1 BTU is 252 little C calories, which would be they give it in foot-pounds too, but that would be 0.252 big C calories. So a BTU is a little bit more than a quarter of a kilocalorie, or a capital C calorie. Okay? So those are some of the conversions that you might just need to keep in mind just for reference points. Okay? That's the mechanical equivalence of heat. Now, let's see if we can find, here's a place. Let's do example 4.4. A 1,000 kilogram car. Let's see, I need a pen. What color you want it? Let's use something light. What color? Second? Seemed like before we used yellow. You want yellow? Okay. We could do orange or light green. Those will work too. So here we have 1,000.0 kilogram car. Now, 1,000 kilograms, there is another kind of common name for that. 1,000 grams is 1 kilogram. What would 1,000 kilograms be? It's a megagram. Mega means 1,000 thousandths, which is a million grams. Okay? There's another more common title for that, and they call that a metric ton. It is a lot. In fact, a metric ton and an English ton are pretty close. Metric ton is about 200 pounds more than an English ton. Of course, a metric ton is measuring mass, and an English ton is measuring weight, but they're still within about 200 pounds of each other out of 2,000. Okay. So this is the mass of, I just gave it away, didn't I? I was going to say, what does kilogram measure? Mass. this is the mass of the car, okay, is moving at 90 kilometers per hour. What is that a measure of? Velocity, okay, or speed, okay. Velocity would be the vector quantity, and since they didn't give us a direction, this is really the speed. And by the way, 90 kilometers per hour, they say in parentheses, is 25 meters per second. No, there's no square. Meters per second is also a velocity. This is velocity of the car. Especially this is the initial velocity of the car, because that's what it is at the first of the problem. How many kilocalories are generated when the car brakes to a stop? So we're looking for kilocalories. Now what's that a measure of? Okay, it's equivalent to a joule, which is a measure of what was the last chapter's title name? Energy, okay? It's a measure of energy. Since your test is going to be on this at the end of the day today, good to know that kind of stuff, okay? So we're looking for how much energy, or in other words, how much work it did. Now, notice they said they're bringing this car to a stop. So what's the final velocity of that car? Yeah, 0, because you brought it to a stop. So then you've had a change of energy. What kind of energy is that you had a velocity associated with it? Kinetic energy. So you had a change of kinetic energy from, and what is the formula for kinetic energy? You should know this one. 1/2 mass velocity squared. Perfect. Okay? So this is going to be, I'm going to write the 1/2 is 0. No, I won't. I'll keep it as 1/2. Okay? Yeah, goodness, it didn't change. Okay. 1/2, the mass of the car was 1,000.0 kilograms. And then what was its velocity initially? Okay, kilometers per hour, but let's use the metric, the SI unit, which is 25 meters per second. 25.0 meters per second squared. Okay, now that's going to be a big number. But first thing I'm going to do, half of 1,000 is what? 500. 500 kilograms. Okay, 25 squared. Okay. You can do it on your calculator if you want to, but that comes up, I believe, 625. 25 times 25, I believe, is 625. Right? Someone do it for me. Anyone got a calculator? Okay. Does anyone have a calculator? Okay. 25 squared. I think it's 625. That sounds about right. 25 squared. 25 squared.
25, I got mine. That's okay. 25 squared.
Okay.
There's 625.
625.
Yes, sir.
What units?
Units.
New. You square meters per second. Meter squared per second squared. Okay? All right. And then we multiply that by 500. And that's kilograms. Okay? And that's going to be, say again?
312.5.
3 what?
I got 313.
313? Okay, I need some more digits than that, folks. 625 times 500.
312.
1250? 12500 maybe? You have 2 decimals there, 2 decimals there, that would be 4 plus another. I think it's got another 0 in it. I think it's something about like that, isn't it? 3 million? Is that right? No, that's too much. You got, that's right. I got off by 1. Okay. Whoa, it didn't erase again. Okay. Let's go back. Okay. You were looking at the book though, weren't you? Oh, your calculator?
I'm just saying, somebody else want to check it.
Okay. 625 times 500. Okay, that would have a 0 there, a 0 there, a 5 there, a 2 there, a 631. Yeah, 312,500. Okay, what units? Kilogram meter squared per second squared. What's that? Joules, exactly. That's a joule. 312,500 joules. But it asks for kilocalories. Okay? Let me scoot back one slide. We'll come right back to this. No, I'm on the wrong page. Okay? Over here. 4.184 joules makes 1 calorie. So 4.184 kilojoules would be 1 kilocalorie. So you could go back here and do a conversion here, and I'm going to do it down here. 312,500 joules multiplied by, and you don't get blank kilocalories. Okay? Now, like I said, if I knew the kilojoules, well, that's what? That's easy to get. How do you get kilojoules? Divide by 1,000. Okay? In fact, we could do that as part of our thing. Let's do it, because that it seems to be, you might be a little rusty on this, so let's take one more step here. Okay? Let's take an extra step. Joules multiplied by, and then multiply it again, and equal blank kilocalories. Okay, so if we could get to kilojoules, well, that's easy. How do we get 312,500 joules to be kilojoules? Divide by 1,000. And here's why. You put joules down here in the denominator, kilojoules in the numerator. 1,000 joules is 1 kilojoule, right? And you divide by 1,000. Dividing by 1,000 is moving the decimal 3 places over. So now you're in kilojoules. Okay, now we want kilojoules in the denominator. We want kilocalories in the numerator. And what was that conversion? Do you remember? 4.184 kilojoules is 1 kilocalorie.
You got times that, right?
Yeah, well, let's go back and see. With kilojoules, that was 4.184 is 1 kilocalorie, right? Let the units help you folks, okay? Cancel out the kilojoules, so you'll take 312.5, because we've already divided by 1,000, when I move the decimal, and divide that by 4.184, and what do you get?
74.75.
Okay, say again.
74.7.
74.7 kilocalories.
Or 75.
Okay, or 75 kilocalories. And the book does, 74.7. Okay, yeah. Now the reason is mostly we had up to 3 significant digits everywhere, so that's why they rounded. Okay, now I've got a question for you. Remember, this is a 1-ton car, approximately. Actually, 1,200-pound car, no, 2,200-pound car, approximately. Moving at 90 kilometers per hour. Now, I'm trying to do this real quickly in my head. Multiply that by 0.6. That's about 55 miles an hour. A car, a little over a ton car, moving at 55 miles per hour. If you were to get out there and try to stop it yourself, if you had a good enough system to do that, you could pull it to a stop or push it to a stop, traveling at 55 miles an hour, a ton car. How much energy would that take? About 75 kilocalories, which also is your capital C calories. And Philip, how much was that drink that you had? How many calories? 90?
No, 290.
Huh?
290.
290?
Milliliters.
Oh my goodness. That would be, you could stop more than 3 cars with just the energy in that drink. Uh-oh. Okay. No wonder that stuff goes right not to using energy, but stored energy, which we call fat. Okay. Yuck. Didn't want to hear that. Okay. All right. So you see how that works. That is not much energy, okay? It is a fair amount of energy, but boy, compared to your drink there, what was your drink, your Lipton? Was that sugar-free or did that have calories? 100 calories. So with that one, you could stop a car in a fraction, okay? That's amazing, okay? So in other words, to burn off the calories you took there, you're going to have to do as much work as stopping a car that's traveling at 55 miles an hour without brakes. I mean, you have to stop it just with your muscle power. Man, I don't want to hear it. Okay. All right, let's go back. Those are our measures of heat. Now, there's another kind of heat I mentioned before, or at least alluded to it before, kind of a little bit. This is called specific heat. Now, I actually participated in an experiment that was dealing with this, okay? Variables that are involved in heating. Of course, you have to have a temperature change to have an exchange of heat, right? Change of energy. You have to have the temperature change. Now, you also have the mass, okay? Remember that liter cup and the little quarter of a liter cup? If you were trying to boil the water in that, the mass, this is much more massive, it's going to take 4 times as much heat to boil this as it is that at the same temperatures, okay? But the other thing that matters is the type of material. Different materials require different amounts of heat to produce the same temperature change. Identical same temperature change. And this little experiment we did, it was a physics meeting one winter, I think it was. And this one team had brought in this device. What it was, it looked like a wheel that may have been about that thick, okay, made out of some type of metal. And all around the wheel, they had drilled in little holes, same size holes. And they had different pegs. They sort of looked like golf tees, but they were uniform. They didn't expand out. Pegs. And the pegs were made out of different metals. There was a copper peg, an aluminum peg, an iron peg. I don't think they had any gold or silver pegs. If they did, they didn't have them for long. Never had them. Okay, and different types of metals of those pegs. And you got to pick a peg, any peg. And there were, I think, about 6 different ones. And we all put the pegs in the hole and sat there and held the peg. Okay, pretty simple experiment. Except in the middle of this disc that they had a Bunsen burner turned on. The flame was heating the disc. And we were holding our pegs. And One guy let go of his. A few minutes later, another guy let go of his, and then another, and another, and another. Were these the wimps, and those were the tough guys? No, the different pegs, because they had different materials, they required different amounts of heat to produce the same temperature change. This one got hot faster because it was copper. Copper is one of the fastest materials to heat up. Iron is much slower. Aluminum, I think, even slower than that. Okay? We'll see that in a minute. The measure of this, of the amount of heat to produce a given temperature change, is called the specific heat. And we summarize it in one equation. All three of those things in one equation. Okay? Before we get to the equation, however, here's an example. Here we have 10 grams of aluminum. Aluminum is a very light metal, a low-density metal. That's why they make aircraft out of it. Okay? Okay? Space shuttles, things like that, very light. 10 grams of aluminum is going to take up quite a chunk here. It's at 20 degrees Celsius. Okay, we're going to heat that up to get it up to 100 degrees Celsius. 80-degree temperature change, right? There's your temperature change. Here's your mass, 10 grams. Okay? The type of material is aluminum. Well, it's going to take 176 calories to heat that up. That's little c calories. Okay? Well, this is little g grams. This is not very much. Or, to cool it off from 100 degrees down to 20 degrees, it's going to give off 176 calories of heat. That's because aluminum has a specific heat, measure of the specific heat, 0.22 calories per gram degree Celsius. So the amount of heat to raise or lower the mass of aluminum at a given temperature, now this happens to be 10 grams and this happens to be 80 degrees Celsius, that's going to be 0.22 calories for every gram per every degree Celsius. Whereas if you had copper, now copper is a lot denser than aluminum, okay? And if you have that copper, it's going to be a smaller amount here, but it's only going to take 74 calories absorbed. So that guy holding on to the copper peg, okay, it's not going to take long at all for that to absorb 74. It's going to take more than twice as long for the aluminum to heat up, so the guy drops that. So it wasn't the WIMP factor, it was the specific heat factor. Because copper specific heat, 0.093 as opposed to 0.22. So that's less than half the amount of heat taken to raise 1 gram 1 degree Celsius. Or 10 grams, 80 degrees Celsius, same deal. Okay? But then what if we had gold? Okay, I wish I did. Okay, 10 grams of gold. Gold is denser than copper, which is much denser than aluminum. And you have that at 20 degrees, heating it to 100 degrees Celsius. That's going to only take 724 calories to heat that. That's about a third of what it took to heat the copper, and goodness gracious, about 1/7 of what it took to heat. No, more than that. No, so 1/7 what it took to do that. So if they had a gold peg, they'd let go of it really quickly, even though they wanted to keep it. Okay, because its specific heat is 0.03. See, less than a third of what it was there, and less than a seventh of what it was there.
Can you use that calculation to see how much it would take to sustain the same amount of heat?
No, that's a different story. That just depends on how well you're insulated and that kind of thing. Yeah. But this is to gain or lose heat, or go up or down in temperature. Okay. So what is the equation? You were wanting it, weren't you? Here it is. Q, which now in this chapter, Q stands for heat. In the next chapter, chapter 6, it's going to stand for charge. Sorry about that. They use the same letter for different things. But capital Q here usually is little q in the next chapter, but they go back and forth. So Q is the amount of heat, is the mass times the specific heat times the change of temperature. Delta T, delta standing for difference. Difference in temperature, initial to final. Okay? Change of temperature. Get to know that equation. We're going to be using it a lot. Not in today's lab, but in Thursday's lab, we'll be using that equation big time. Q is equal to MC delta T. Now, not only that, but we could, if we wanted to, solve for one of the others. For instance, what if we wanted to figure out what the specific heat was? Well, then we divide both sides of the equation by M delta T. And by the way, capital T is usually temperature, little t is time, so get that straight too. And that would be M delta T here. And the M's go out, delta T's go out. That would give you C. So specific heat, and this is how they determine it. It's the amount of heat that's gained or lost when you have a certain mass of material changed in temperature a certain amount. That's how they get C. But what if you wanted to know the mass? Then you could divide by C delta T. So then you'd have mass is equal to Q over C delta T. Okay? What if you wanted to know delta T? Then you would have delta T is equal to Q divided by CM, MC. MC, we'll put it as MC. MC. Let me rewrite that.
Can you put that in the circle equation thing?
You kind of can. You just have to be pretty careful. I'll show it to you in just a second. You now have three things on one and one in the other. So if you like the circles, then what you do here, there's your dividing line. Q goes up here because it's always on top, but now you have three multiplications. Okay? You'd have to do that. M, C, delta T. Okay? And you see you get them. If you're looking for Q, it's M times C times delta T. Right there. If you're looking for M, like we did here, it's Q over C times delta T. If you're looking for C, like we did here, it's Q over M times delta T. And if you're looking for delta T, it's Q over M times C. Yeah.
It's easier for me to,
What's that?
it's easier for me to comprehend it that way.
Yeah, but you have to remember there's three things on the bottom and not just two on the bottom and one on top.
MC are different per second. Math.
Yeah, mass is down there with C delta T. Yeah. Mass, specific heat, and change of temperature. Okay. Any more questions? That's a good point. Okay. Now, before we get into heat flow, let's look at example 4.5. And let's go back and find the clean page to work on. Here's one. So let me get rid of my writing here. Though I probably need something there. Let's erase all ink. Let's see, can I go one more? No, I can't. Okay. How much heat? So what are we looking for? How much heat? What stands for heat? Q. Okay, so Q is your unknown here. That's the question. How much heat? Must be supplied to a 500 gram pan, 500.0 gram pan. What's that a measure of? That's your mass, okay? To raise the temperature from 20 degrees to 100 degrees. 20.0 degrees Celsius to 100.0 degrees Celsius. What's that going to produce? What is your delta T? Delta means difference. 80. It's a difference between these two. So your delta T, this means that delta T is equal to 80.0 degrees Celsius. Okay? And the A part of this says, and by the way, time out here, you need to flip a page. Okay? And I wish they had shown this first, but I don't even think they've got it in the slide set. Shame on them. They ought to have it in there. Here is your table 4.2 of specific heat of certain selected substances. Now this is just a small handful of substances. Air has a specific heat of about 0.17. Okay, fairly small. Aluminum 0.22, bigger than air. Okay, concrete just a little less than air, 0.16. Copper 0.093, very small. Glass on average about 0.160, so that's about like your concrete. So basically the amount of, to heat the concrete blocks there and the glass is going to take about the same amount of heat per gram. But the thing is, concrete blocks weigh a lot more, so the glass will heat up a little faster because it doesn't weigh as much. But that's a different issue. Okay, gold 0.03. It doesn't take much heat at all to warm that. Ice 0.5. Boy, that's the biggest yet, isn't it? Takes the most heat. Now this isn't talking about melting ice. This is to change the temperature of ice 1 degree Celsius, which may be from negative 7 degrees Celsius to negative 6 degrees Celsius. It's going to take about 0.5 calories for every gram per every change of degree Celsius, or kilocalories for every kilogram change of degree Celsius. Okay? Iron 0.11, we're back down there, less than air, less than concrete, less than glass, but greater than copper. Mercury 0.0305, my goodness, that's just a little bit more than gold, but not much. I'm sorry, that was lead, 0.0305. Mercury is 0.033, so that's just around gold, a little bit higher than gold. Seawater, oh man, look at that one, 0.93. It takes a lot of heat, a lot more heat to heat water than it does everything you saw before there. The next closest thing was ice, which is another form of water. Silver, 0.056, that's down there between mercury and copper. Soil on average is 0.2. Air was 0.17, so they're not far apart. Steam, look at that one, 0.848. That's right up there with ice and almost as much, not as much as seawater. And then water, look at that, the highest, 1. And that's, why is it 1? That's how we came to name a calorie. How much heat is taken to raise 1 gram, 1 degree Celsius. So that has to be 1 on the nose. See, it's the basic stuff for most of the things we measure. It's the standard water, okay? Now, what that indicates, water has the highest specific heat of just about any material on the planet. There are a few, like helium is greater, but who has a lot of helium around? And it's a gas anyway. So most materials, water has the highest specific heat. Where are some places we use that fact? No, Heidi knows. The fact that water has the highest specific heat. What do we use water for? In your car.
Radiator.
Radiator, exactly. It's pulling the heat away from the engine. If you didn't pull that heat away, the engine's going to melt or warp or something, right? So you have to have coolant in there. Nothing cools better than water. So they use pure water? Not really. Why not?
Free.
Second?
Free.
Because when it gets cold enough, it will freeze. And water, unfortunately, one of the few materials on the planet, expands when it freezes, not contracts. And you could bust an energy block if you have water freezing. You didn't think water was that strong? It is. Okay? So they put antifreeze in it. Well, why don't you just put pure antifreeze and not have to mess with water? Because antifreeze doesn't have as high specific heat as water. You need some water in there. Now they also put a material in there to cut down on rust. If you were to put pure water in that hot against the metal, you're going to produce a lot of rust. And the antifreeze also helps you from rusting out your engine block as well. Now that's just one example of the high specific heat of water. Have you ever been down to the beach in the summertime? Okay? And I tell you, I swear, when you're driving down, it gets hotter. I know until you get to Montgomery. Montgomery's almost always hotter than we are here. And I think even as you go further down, it keeps getting hotter. But then when you get right on the beach, suddenly it feels cooler. I wonder why. The water has a higher specific heat. It takes more calories to cool the water than it does to cool the soil. That's 0.2. 5 times as much heat to cool the water as it does to cool the 1 degree Celsius. Air, even more than 5. So yeah, that's why the water is cooler. But if you go down this time of year or a little bit later to the beach, it's warmer because the water is giving off heat, because it takes 5 times as much. It holds 5 times as much heat, so it's giving off heat all the time. Water is our best regulator of temperature. Okay? Now, unfortunately, another good regulator is ice, because you have to melt ice too. Okay? But guess what we're doing to our ice caps? We're melting them. So when they get more melted, then we have less buffer. So the colder part of the planet gets actually colder, and we get warmer because
Climate change.
you got it. Okay? A lot of people say it doesn't happen. It does. Okay? Study the science. Okay. Anyway, I wanted to show you the table so we could do this exercise. So what if this material is iron? I'm going to abbreviate it as Fe. That's the symbol for iron. Okay? How much heat is given off? Do you remember what our one equation was we summarized? Q is equal to MC delta T. The M we have is how much? 500.0 grams of mass. What was the C for iron? That's where you turn to the table and see what you get. 0.11. But you need units. What are they? Calories, little c calorie, per gram degree Celsius. Multiply that by delta T, which is 80 degrees Celsius. 80.0 degrees Celsius. Guess what happens? Your grams cancel out, your degrees Celsius cancel out, you're left with calorie. Is that a good thing to measure heat in?
Yeah.
Perfect. So, get your calculator. I think we can do this one in our head. 500 times 80 would be 40,000. 40,000, and multiply that by 0.11, and that would be a 0, there goes your point. 4,400, right? 4,400 calories. That's how much heat it would take to heat 500 grams, which is a fair amount. 80 degrees Celsius, that's a pretty far amount. Okay, so 4,400 calories. Now, what if we wanted to use a smaller number but a bigger unit? What would you use? And how much would that be? 4.4 kilocalories. So if you're trying to measure that in food calories, what would that be? Also be 4.4 capital C calories. That's what a kilocalorie is, a capital C calorie. We don't usually do that, but I was just pointing out to you, that's not a lot. You just ate with probably a couple of potato chips. You ate that many calories. All right? Okay. It's amazing. All right. But the B part of this problem said, what would the, here it is, if it was made out of aluminum? Well, everything else in the problem would be the same. This is Q for iron. So that would be Q for the iron would be 4.4 kilocalories, or 4,400 calories, little c calories. For aluminum, the mass is the same, 500.0 grams, but C changes. What would C be for aluminum? 0.22 calories per gram degrees Celsius. And we're also changing that the same 80 degrees Celsius. Whoops, I left off C. The grams go out, the calories, the degrees Celsius goes out, you're left with this. And what would that be? 8,800 little c calories, which we could write as 8.8 kilocalories, or big C calories. Okay. That's still not close to one bottle of thing. If you were to rub your hands together enough to make that change. Okay. And that's what they got. 4.4 kilocalories and 8.8 kilocalories. Now they have another example at the bottom. So it's all right for me to erase this? Okay. What is the specific heat? So this time, what are we looking for? What is the specific heat? What symbol is we use for specific heat? C, okay? C is what we're looking for now. Now, C is also used for the speed of light, but we're not using that C. We're using specific heat now. Again, we use the same letters over and over and over. Okay? What is the specific heat of a 2 kilogram metal sample? What's 2 kilogram a measure of? Say again? What does 2 kilograms measure? Two kilograms. What does that measure? Mass, not weight, mass. Okay, that's your mass. If 1.2 kilocalories is needed to increase the temperature. So 1.2 kilocalories, what's that measuring? Say again? That's your heat. What symbol is that?
Q.
Q. Very good. Okay. To increase the temperature of that metal from 20 degrees Celsius to 40 degrees Celsius. What's that telling you? 20 degrees Celsius to 40 degrees Celsius. And that's, oh, I forgot to put my C in there. That produces what? Huh? And what is it? That would be 20.0 degrees Celsius. That's your change of temperature. So you're looking for specific heat. C. Do you remember which rendition of our formula would give you C?
M times.
Say again?
Q divided by
Q divided by
M.
M
Times. No,
the other thing?
delta.
Delta T. Change of temperature. Okay? So you already know this Q, that's 1.2 kilocalories, divided by the mass we had as 2 kilograms, and the delta T we found out was 20.0 degrees Celsius. Okay? Let's see what we get. 1.2 divided by 40. Pretty small number.
1.2 divided by 40.
Yeah.
I got 30,000. Oh no, Nick, I apologize. Nick, it's million.
Okay. 0.030 is what you said. 30 thousandths, which is 0.0. And what would that be? In what units? No, kilocalories per kilogram degrees Celsius. Now you could leave the K's in there or divide them out and make calories per gram degree Celsius. You'll notice in the table over there, they listed both, either calorie per gram degree Celsius or kilocalorie per kilogram degree Celsius. So yeah, we got it. What material might that be? Say again?
I said goodness.
Yeah, that'd be,
Wood?
I don't think so.
no, sir. No, sir.
I don't even see wood on here.
Oh,
Gold! Hey, let's see, 2 kilograms of gold. I'll take that and go home.
yeah.
All right, that's going to be quite a haul right there. They make us drool, don't they? Okay. Now, I think they've had a little series of kitchen physics. This one's pretty interesting. Consider the following information as it relates to metals of cooking pans, pots, and pans. Now, what was the material that had the least specific heat? Yeah, look at that table above. Smallest specific heat. You just did it. Gold. Okay, so they make most of your pots and pans out of gold, right? Oh, no, that's only in Trump Tower. No, I'm sorry, I didn't say that. Okay, sorry, okay. No, we probably won't find much of that. Next smallest?
11, iron,
Below that.
Aluminum?
Second?
Aluminum?
Below that. Small.
Silver?
Second?
Silver?
Silver's pretty small, but there's 2 below that.
I'm gonna say.
Oh, mercury.
Is 1.
Mercury and lead.
Lead is next smallest, all right? Just above gold. You make many pans out of lead? Why not? Yeah, it's toxic. It's a heavy metal that you don't want to listen to music. No, I mean, that's not a different guy. Okay, it's a carcinogen. So you don't want to cook out of lead. No, let's not do that. Okay, what was the next one after lead?
Maybe we could say,
That'd be mercury.
Mercury. Okay, how many pots or pans are made of mercury? Mercury. Why not?
Another toxic metal.
Okay, but what's more? It's a liquid. Okay, you can't make a pot and pan out of it, not to cook in anyway. Okay, so lead's out, mercury's out. Okay, next to that, you named it.
Silver?
Silver. All right, yeah, that'd be a great one. Yeah. Only in the Queen's Palace. Okay, never mind. No, I can't afford that one. Okay, then after that.
yeah, I say copper.
Copper, you got it. And haven't you seen some of those pans that are copper on the
Yes.
bottom?
Yes.
That's why.
Yes.
Because it takes less heat to heat the copper so you can cook your food faster. That's it. So, the question here is, consider the following information as it relates to metals of cooking pots and pans. It's easier to change the temperature of metals with low specific heat. It's harder to change the temperature of metals with high specific heat. So look at the list of metals and specific heat in that table above and answer the following question. Considering the specific heat alone, which metal could be used for making practical pots and pans that are most energy efficient to use? You've already answered it. Practical? What did we finally decide on?
Iron rod.
I'm just a question.
Copper would be the best.
Copper.
Remember, that's the one that, yeah.
Yes, sir.
Copper would be the best. After copper, not far above it, is iron. And guess what we use a lot in cooking? Cast iron. Yeah, those old pots, pans, they know how to cook. Okay, especially if you season them right.
Still around.
Yes. Okay. And next after that, practical stuff. We don't use much concrete for our cooking, so let's not use that one. Air wouldn't be very practical at all. But there's glass. Now that's an average thing. and you do use Pyrex glass. Now, a lot of glass, just, any old glass you don't put in the oven because it's going to shatter. The Pyrex glass will hold together well, so that's not bad. Okay, usually don't do on the stove top with it, but you can put it in the oven. But then after that,
Soil.
say again.
Soil?
Okay, I don't want to use much soil to cook my food on. You can yours, but not me. Okay. Yep. And then finally we get to aluminum. And sure enough, there are a lot of aluminum pans. A lot of women like them because they're lightweight. They're not as heavy to use. But then on the other hand, you got a higher specific heat. So it's going to take more heat to warm it up. Oh, and look who snuck in on us, okay? Lakeisha's here. Boy, the bottom part of the alphabet's doing really well. Michael's the only one missing. See, I guess the other way we could say this is the non-automotive students are doing pretty well. We only got a couple of them here. And of the automotive students, we're glad y'all are here. Though. Okay. Again, considering specific heat alone with certain combinations of metals provide any advantages for rapid temperature changes. I don't know. Those pots and pans you see, they are usually copper on the bottom, but then something else on top. I don't know exactly why they do that, except maybe to keep the handle from getting as hot. I don't know. What?
The copper on the bottom, it heats up the metal.
Right, I understand that. But why do they have something else on top? Maybe it's a cheaper metal. Cheaper, okay, got it. Okay.
I'm guessing.
Okay. Okay. Now I think we're ready to go to heat flow. All right. Now y'all keep me up with what time it is. Okay? Heat flow. 3 mechanisms for heat transfer due to a temperature difference. Anytime you have a temperature difference, you're going to have heat flowing. Now, remember, wait. Heat is not a material, so it really doesn't flow. But remember, they thought it was a material for so long, we still use the terms as if it flowed. It doesn't, okay? Heat transfer is the better word. These 3 are conduction, convection, and radiation. And we'll talk about what conditions are most favorable for these, what materials that happens best in. We'll talk. Natural flow, and this they've said it before, they say it again, natural flow is always from high temperature to regions of cooler ones. That's where heat flows. Down a gradient, a heat gradient, from high to low. Everything does it like that, okay? Down a gradient. So let's talk about conduction first. What do we mean to conduct heat? Conducting heat. That's heat flowing through the material, okay? We'll show a picture of it in just a minute. In fact, let's show it now. All right. Here we have a metal rod here. I guess it's metal, some sort of rod. And you put a Bunsen burner under one end of it. And you have thermometers stuck in the metal periodically. Before you turn the burner on, okay, you all these were at the same temperature, right? Not too bad. You turn that Bunsen burner on, this one's going to go up first, that one go up not quite as much, and not quite that, but in time they'll all rise. Well, that's because the heat is being conducted through the material. It gets to this one first, then it gets to that one, then to that one, then to that one. After a while, they all get to be the same temperature, but you can see the heat flowing on those thermometers because the temperature is going up. Okay, the mechanism here, what's going on? Well, what is temperature? Temperature is a measure of the average kinetic energy of the material, of the molecules. Kinetic energy is related to what quantity? 1/2 What? You told me earlier.
Mass time velocity.
Squared. Okay? So it's velocity. So what's happening here, you heat up this metal at this end, and the molecules start moving faster, bouncing into each other with more energy, more kinetic energy. They bounce into these molecules, into that one, into that one, into that one, and so these are measuring higher temperature. And then this one, that measures higher temperature. And it goes down the line like this, but these are getting hot faster because they're closer to the heat. That's what we have. That's the mechanism. The hotter atoms collide with the cooler ones, transferring some of their energy. Direct physical contact is required. You cannot have conduction in a vacuum. Okay, we'll talk about that in just a minute too. So you have good conductors and you have lousy conductors. Okay, the poor conductors are sometimes called insulators. Okay? And what are some of those insulators? Styrofoam's a really good insulator. Okay? After that, wool is pretty good. Air is a very good insulator. Okay, so we're going to talk about these in a little bit. The key here is that this is heat flowing through matter. Okay? And if you can do anything to block the heat flowing through the matter, then that's a poor conductor, which is a good insulator. Okay. Now, what's happening here, as we said, the hotter atoms here on this end, where that heat is making them move faster, but it's in a metal, so they're in that lattice. Well, they're moving and bouncing into their neighbor and bouncing into the neighbor. These down here have hardly felt a thing yet. A little bit, but not much. These up here have felt much more, that more. The average kinetic energy, that's what temperature is measured, of the molecules. And that's what's going through this. Okay. Now, which materials would you think then would be your best conductors? Solids, liquids, gases, or outer space? Which would be the best conductors in general? Solids, because they have this 3D crystalline structure here, they're going to communicate a lot better. Now, of the solids, which one do you know conduct better? You've experienced this before. If this was a metal rod here, and you're holding it here, you're going to let go in a while. Because, yeah, okay. Very good. Okay? Now, if this were a Pyrex dish, you can hold on to that a long time. In fact, I've seen a picture of a Pyrex dish frozen in ice, and half of it sticking out here with a Bunsen burner over it, and it's not melting the ice, because the Pyrex does not conduct well. Now, the reason for that, metals have what we call free electrons. Now, we'll talk about this in the next chapter too. Free electrons. It's not the molecules vibrating that carries the heat, it's those electrons. The electrons are very light, very mobile. Okay? Those free electrons. That's why metals are good conductors of heat. And guess what? In the next chapter we're going to find they're also good conductors of electricity. Exactly. For the same reason they have free electrons. Okay? So what's usually your good conductors? Now, your lousy conductors then would be, what did you say was the best materials for conducting? Okay, yeah, your metals, and those were solids. Your worst were? I gave you 3 phases. Solids, liquids, they're not as good, and gases are not as good. So gas, there's air right there. Okay? Now, I see you have on a sweater tonight. You're used to this room being cool, aren't you? Okay? Now, why does that keep you warmer?
No, you got holes in it.
Okay, but it's got holes, but guess what? Those holes trap air. Okay? Well, any kind of air. Air is a good insulator. And if you think about it, that looks like maybe a cotton that you have on. Okay, that traps fairly well. If it were flannel or fleece like yours, that's better because there's plenty of place for it to trap air. Okay? Let's think about the insulation in your attic. What is that like? Now, in our old house, it's, I think we called it rock wool. It's that gray-looking material, but it trapped air in between. Better than that is styrofoam, or what do they call that? Fiberglass, because it traps a lot of air in between the fibers. That's your good insulation. Okay? Now, let's think about, any of you have a Yeti? You do? Okay. How good is that? Oh, man. How does that work?
It contains heat or cold for
A long, long time. Hours and hours. What it does there, but it says a vacuum is the least. You can't get any heat through a vacuum. And basically, between the walls of that Yeti and the old thermos bottles, which is like what it's like, you try to evacuate the air. And therefore, there's nothing to conduct the heat. So that's why a vacuum, as in a thermos bottle, a Yeti, I think is pretty much that too. It has really, really good insulation. Okay. I think we've knocked that down, haven't we? Okay, so that's conduction, mostly through solids. That's the best conductors are solids, and the best of those are those with free electrons, which would be your metals. So those are your good conductors. Anything else are poor conductors or good insulators. Oh, and by the way, have you ever, we don't get snow here much, okay? But when we do get a snow, do this the next time it snows. Drive down your street and see which houses the snow melts the fastest on the roof.
Yeah, because their insulation is
Because their insulation's
They got
poor.
cheap insulation.
Okay, yeah. And you hope it's not yours. If it is yours, then I would say put some new insulation in your roof.
If
Okay.
it melts,
Yeah.
If it melts fast.
Keep your roof.
And you'll also, I think you'll notice this sometime.
The heat
Have-
bill will be high too.
Yeah. Have you ever seen these houses that the snow is all piled up on the main part of the house, but then the sunroom over here or the family room or something is hardly any snow on it at all? And you know what? The likelihood that used to be a garage.
Right. No
And
insulation.
then what they did when they closed it in,
It's pretty
you got to
rough.
put insulation. Because you don't insulate a garage most of the time. Why? But they forgot to put it in, and then you got poor insulation in it. And a lot of those sunrooms, my older brother, the house he owned, he and his wife had in Dublin, Georgia, that big playroom sunroom, it wasn't called a sunroom, playroom or den or something like that on the edge. It was always freezing in there because it used to have been a garage, and they just closed it in but didn't put insulation, probably either in the walls or in the ceiling. Cold room in the wintertime, and probably really hot and hard to cool in the summertime. Okay? What's that?
My bed downstairs be cold, but it's up under my kitchen.
It's what?
It's under the kitchen.
Okay.
But so why does that be cold? Why is it cold?
Okay. Is there any exterior wall? Or is it all in the basement?
It's under the ground.
Underground.
Mm-hmm.
My guess maybe is that you don't have good ventilation in your heating system. Not as much.
Only one vent down.
Okay, that may be it. And do you have a return down there too?
No.
No. So there's nothing to pull the air out
Okay.
except somewhere way upstairs and very little. So that's probably it. I'm guessing. Just guessing. Because really the soil makes a pretty good insulator too. Here are some of these materials. Here they have the conductivity. They didn't have the specific heats. And one of the best conductors is silver. Okay? Relative conductivity, 0.97 out of 1. That's really good. Right below it would be copper. I don't remember what copper is. Let's see. I think these are in your book. Yeah, it has it in your book. Right below it is copper at 0.92. Okay? And right below copper would be aluminum, 0.5050. After aluminum would be iron. And there they have iron, 0.11. These are conductors. And later in chapter 6, next chapter, when we talk about electrical conductivity, you'll see the same order. Okay? Water, a really lousy conductor. Okay? A decent insulator. Okay? They have a few other things in between. Lead, 0.08. Concrete, 4.0 times 10 to the minus 3. Not a good conductor. So concrete's not good. Glass, 2.5 times 10 to the negative third. Tile, 1.6 times 10 to the negative third. Brick, block, 1.5 times 10 to the negative third. Water, 1.3, they have that one there, times 10 to the negative third. Wood, 3.0 times 10 to the minus 4. And the units, these are just relative units. So wood is a pretty lousy conductor. Don't show it here. This is about the time for playoffs, isn't it, in football? High school playoffs? Aren't they still going on? Okay, it's getting pretty chilly out there. In fact, I remember in our high school team, it got so cold out there in the practices, I was beginning to hope we didn't make it to the next round because it was really cold out there. But if you're going to watch the game, you're not even able to move around then. And some of the stadiums you might go to, and back in the day when I was there, they had these nice, new, fancy aluminum bleachers, and then they had the old wood bleachers. But this late in the season, guess where I wanted to sit? The what? Why? Okay, it wasn't any warmer. It's the same temperature as the outside air. But it felt warmer, didn't it? You know why? You sit on that aluminum bench, and aluminum's a good conductor. It's taking the heat away from you, and you're feeling the air temperature. You sit on the wood, which is a good insulator. It rapidly comes to your temperature because it's not taking it away. It feels warmer. You're warming the wood. It's not warmer than you're warming it. You can't warm aluminum till you warm the whole seat, and it takes a while. Okay. That's what's happening. It's conductivity. It's not that the aluminum's colder. It's the aluminum conducts the heat away from you faster. Okay. Then you've got cotton. Okay. And generally this is cotton, but it's sort of a knit. So it's warmer than most of the shirts I've worn. Those thin shirts, they don't. I can't stand it in here with those. Okay. Styrofoam, a really lousy conductor. 1 times 10 to the minus 4 relative. That's 0.0001 as opposed to 9.97. So it's really lousy. Glass wool, that's what's up in our attic. 9.0 times 10 to the minus 5. That's almost the same. And then air is 6.0 times 10 to the minus 5. And vacuum, absolutely 0. Nothing is conducted in a vacuum. There aren't any molecules that bump into their neighbors, so you can't conduct any heat there. Does that make sense? All right, good deal. Okay. They have a nice picture in your book. Okay, couple of things. The required insulation of Science and Society. Can you spend too much for home insulation? That's a good question. That's a very short little thing. Read that, see what you think. Now, there is a point of diminishing returns. You won't get as much thing to put an extra inch up there than if you already have 6 inches of insulation, put one more. Not going to make a lot of change. So it might get to the point, say, I'm not getting my money's worth to do anymore. But there is some minimum amount that you need to have up there to protect. And the house we built over on the farm in Georgia, that place, even though it wasn't all that well constructed, we saw them when they were building it. They did put the insulation in because we were watching when they did it. We insisted they poke it into the corners back there. That house holds the energy really, really well and warms up. Like we went over there on Veterans Day because I had the day off, and it was chilly in the house because it had been cool that night, and it was maybe 70 outside. And so we just opened the doors and it warmed up fairly quickly. But when we did have to turn the heat on, it didn't take long at all. Of course, it's a small house, but the insulation's good. And the windows are thermal windows. Those are not, okay? These walls here, no insulation in them. Those are concrete block. Outside is brick, okay? That's just a facade. There's no insulation. Modern construction, you'll see them put up things like styrofoam sheets or other things like that to in between the outside face and the inside face of the wall. That's insulation. Okay. Concepts applied. They mentioned touch temperature. Objects that have been in a room at constant temperature for some time should all have the same temperature, but touch them and they feel like they're different, just like the seats at the football stadium, because some of them are conducting your heat away, others of them are trapping the heat against your body because they don't conduct. All right, so that's conductivity, the first of your three forms of heat transfer. The second of these is convection. Does anyone know what this means? And how are we doing on time, by the way? It's 5:12. You've got about 3 minutes. Okay. Are we going to be able to get through convection in 3 minutes? Probably not. Okay? So you want to just pause it here. I'll stop the slideshow and we'll pick up with convection next time. I wish y'all have to remember conduction because we want to compare and contrast these later. So we'll pick up with convection next time. Okay? Now, I'm going to pause this. Okay, what we've done so far is I've given 2 thermometers to each team. We only have 4 teams in here. 3 of the teams have 2 people each. 1 team has 3 because we have an odd number. They've got their thermometers in ice now. And the ice, some of it is melted, so at the bottom they're in water and they're measuring when you think it's reached its minimum. Okay, if you pull it out, your temperature's going to go up. So be sure to keep it down there in the ice water. It's okay. Now, there is a little bit of a problem with having it either touching the bottom or touching the side, so I would scoot it in just a little bit. Okay? Don't have to touch the bottom either. Just a little off the bottom. You can't keep it. Okay. It'll be okay. Okay. Yeah, it will touch the bottom. I would say scoot it off the side a little bit. Okay. And let me know when it seems like it's quit dropping in temperature, because it was room temperature before you put it in. It's been dropping a little bit. Now, while they're doing that, what we did was measure the atmospheric pressure. Someone on this phone found that it was 29.23 inches of mercury. We converted that to millimeters of mercury by multiplying first by 2.54 centimeters in an inch, and then multiplying by 10 millimeters in a centimeter, and that gave us 742 millimeters of mercury. That was 16 millimeters of mercury below normal, which is 760 millimeters of mercury. So then we multiplied that 16 millimeters of mercury by 0.037 degrees Celsius for each millimeter of mercury, and that gave us we're going to use later, not now, negative 0.592 degrees Celsius. Okay, I'm just doing that for screencast-o-matic. Have they stopped dropping in temperature? What? Okay, did you measure your temperatures before you pulled it out? Okay, measure them. Once they quit stopping, now that you pulled it out, you might have to let it quit dropping again. But what you're measuring now is on page 152. That is your observed melting point. Are you able to see your observed melting point? Okay, record that on your page 152. You've got one thermometer 1 and one thermometer 2. Put them down for each of them. What's that? Negative 14. Something is screwed up with that.
Where do we put it on the sheet?
That is weird. Okay, that's supposed to be right. That's supposed to be right. Okay, this is something seriously wrong with that.
0 and 2.
I have never seen that happen.
3.1 is.
And your team too? I'm going to go get you another thermometer. Yeah, one right here. Okay. No, there's something seriously wrong with that. Whoa! See, jungle. Have this be your cycle. Take the other one out and give it to me.
This measurement is just right
Okay,
here.
well,
Measuring.
Okay, now you put what you measured in there. The thermometer 1, thermometer 2. Rather than try one. Bad guy. Okay. I don't know what's happening with that. That is bizarre. What's that? Okay. What were some of the temperatures you were measuring? Right on the 0 button? Okay. Then that's what you put. 0 for observed melting point, 0 for trial 2 or thermometer 2. Change those trials to thermometers 1 and 2. Your measurement error, but we know that melting ice is at what temperature? Celsius? 0 Celsius. So you have 0 measurement error on those two, on the lower scale. Okay? Now, if you've taken your thermometer out after you got those temperatures, put them in the boiling water. Okay? Put them in the boiling water.
So the observed melting point was 0.
What's that?
Ours are 0.
Okay, were they both at 0?
One was at 2.
One was at 2, the other, which one was which?
Point 1. Point was 0. Or 3.1 was 0 degrees Celsius. 3.2.
Okay, mark it that way. So, thermometer 1, thermometer 2.
Okay. So the 1 was 0.
Okay.
Measurement error.
Okay. Your one that had the 0, is that the one? Yeah. Your measurement error is 0. The other one was plus 2. Degrees Celsius. Okay, yeah, put them in the boiling point. Now, if that water quits boiling, let me know. Okay. The other thing, right before you make your measurement, once it finishes rising a little bit, then what I would do is lift them off the glass and measure it at that point. You know. Lift it up so it's not touching glass. This is more important than the ice.
That's the, no, which one, that's for the boiling water, right? Number 2
Both
is
of them?
102.
Yeah.
And then, let's see,
Under observed boiling point.
yeah. That's what I'm just asking, if you want to put it up on the,
What's that?
put it up on this, right?
Okay, yeah, this is thermometer 1, thermometer 2. Okay, you got 0 and that's 2.
Okay, yeah.
Okay, so the expected was 2. Okay, and observed boiling point.
Well, my number 1, I have to check now.
Okay. Y'all got yours in there? You already made the ice measurement yourself.
So we need to write the same.
What's that?
I mean the same.
Sorry. Yeah, your thermometer is right on 0. You had no error. Okay. Degrees Celsius. Okay. Both of them are 1 and 2. So.
Yes.
Okay. Then you have to account for the barometric pressure. So you put barometric pressure as, and I would say you got room on that, put 29.23 inches of mercury, and in the same block, put 742 millimeters of mercury. Okay, that's your expected value for melting point would be 0. So that's 1 degree off, so it's a +1 measurement error, and that's 0 degrees off, so that's a 0. Yeah, well, it's listed measurement error. So +1 degree Celsius.
So you said for the barrel,
That one you can put 0.
so you said for right here, we put 2.
Okay, barometric pressure, put 29.23 inches of mercury, but then also in the same block, put 742 millimeters of mercury. That's why we did that.
So don't put 44.44.
I'm sorry.
Yeah.
Wait, I messed this up.
Okay.
This was 7. Okay, we got to go back and do another calculation, folks.
Okay.
We were 18 millimeters of mercury off. 18 times 0.037. Go back and redo that. I'm sorry, I thought I missed
You what?
Gosh.
Say it again.
Calculate. Give me the numbers to calculate, Mike, please.
0.037 times 18.
0.666.
0.
Say again?
0.666. 0.666.
Oh, you got it.
Point 6.
666. 3 sixes.
0.666.
Wow, not a nice number.
Not at all.
Okay.
Going home.
Oh, I got it.
All right. I didn't know 2 degrees would do that to you. But yeah, I guess it will. Okay. So now what we'll have to do. Okay. So in the barometric pressure, you got a big block there. You can put 1 in either block. It doesn't matter. But the barometric pressure is 29.23 inches of mercury, which is 742 millimeters of mercury. And then deviation from normal, that will be minus, and here you put both these, put minus 18 millimeters of mercury, but also put in that same block
0.
minus point, and you can put 0.7.
And that's for number 2, right?
Both of them. Trial 1 and trial 2.
So you want to write both of them in the same block? So you just, I put that there.
That's good.
And then put
You
the
can put the
other.
same thing there too. No, barometric pressure, that's what the barometric pressure is. That's in inches of mercury, that's in millimeters of mercury. Yeah. One team still has, or 2 teams still have.
Oh, let me pull it out. Uh-oh. Sorry.
All right. Have you read them?
Yeah, I read it.
Okay. And the other team? Okay.
Those are 2 right here.
Okay. All right.
Are we supposed to write the 0.6 and the deviation from normal?
Okay, the deviation from normal, I would put minus 18 millimeters of mercury, that's your barometric pressure, but I'd also put minus 0.7 degrees Celsius. Now, why not do 0.6667?
We don't need that, man.
Huh? You can't read it anyway. I doubt if you can read 0.7, but write it down. Negative 0.7 degrees Celsius. Biggest I've ever seen. So what would be the accepted boiling point then? 100 minus 0.7, which would be 99.3. Right?
Exception.
Because you subtract.
What's that? Oh, okay.
9.3.
Now, that's what you expect your thermometers to read. What did they read?
Well,
You already put down your observed boiling point. The difference between your observed boiling point and your accepted boiling point, which is 99.3, and that would be your measurement error.
we had for the first one, 102.
I don't know what yours was, but whatever it was.
He accepted the boiling point is 100.
No, the accepted boiling point would be 100, except for barometric pressure, you have to subtract off 0.7. So that would be 199.3. That's it.
Yes.
Okay, and then you measured this subtract that, and that's how far you're off.
Okay, then, 102. So that's,
Okay, everybody's got all what you need out of the, yes. Right.
okay, then I put my results on here, so I can put 1.7 here. You subtract from here. 99.3 from the 102. And what both yours would be there. But you know, you put 99.3 here. What was the second one that you subtract from here? Both of them 99.3. So that's you right there and that box. And then what you subtract from these two, that's your answers for the next. So both of them is 99.3 in the box.
Okay. How y'all doing? Okay. Now, what I want you to do, before we do any more, okay, what I want you to do, before we go to results, and going further, we're going to do both of those, but there's a little invitation to inquiry on here. Okay, and if you'll notice this on page 151, wash an aluminum pop can. Obviously, this wasn't written by anyone here in the southeast. That would be a pop can. Okay, yes, okay. Leaving a small amount of water in the can, which I did. And if you'll notice the can back there, you can see a little bit of steam coming out, can't you? Okay. Use tongs to hold, don't touch it because it's hot. Use tongs to hold the can over a heat source until it boils. You think it's boiling? Can you hear it?
Yeah, I see the little boats.
It is, okay, so it is boiling. And you can see steam condensing in the air above the opening, can you? Okay, good. Now, here's what I'm going to do. I want y'all to all come back here and watch. Okay? What I'm going to do is take this can, can you all see? Okay? And I'm going to take it and rapidly, what happened? Okay, why? Huh? Okay, temperature change was part of it. That doesn't make the can collapse.
The pressure, it was.
Oh, pressure. Why pressure?
Because of the different temperature, the pressure, because it was hot steam, the steam.
Okay. It was hot, and you're absolutely right. A lot of the water was steam in here. when you invert it over the ice water, now all of a sudden that, number one, the steam cools greatly, which reduces its volume, but even more, some of that steam condenses back to water, going to a very small. So now you have a smaller volume inside the can, so therefore there's less, okay, and therefore the pressure outside the can was greater. That was atmospheric pressure. Inside the can, the pressure was reduced. That's what collapsed the can. Did you think it would do that much? Pretty amazing. Yeah. Okay, so y'all can, that invitation to inquiry, and answer as much as you can there.
So what's he writing?
Okay, right. You don't have much room, but
Yeah.
it says, okay.
So what we put, what did I say? The pressure.
Okay, it says, explain what happens in terms of Charles's law and Boyle's law. Hey! 10 o'clock scholar! Okay, you have to get the data from somebody else. And let me mark you here. And by the way, I forgot, what time is it now?
6:05, 6:07, something.
Okay, so we're into the lab time now. Okay, so Zach already marked some of these, but I've got Wayne here now. Parker hasn't come in, Lacey hasn't come in, Tristan hasn't come in, Will hasn't come in. Emmanuel left, didn't he? Siegfried's still here. Michael is still here. Patrick is still here. Lakeisha's still here. Philip's still here. Heidi's still here. And Amika's still here. Yes, sir.
What experiment am I missing? I know I'm missing.
What's that?
I know I'm missing the experiment from last Thursday, I think.
You don't have that one?
I think that's the only one I have. I don't have.
Okay.
I think it's third.
Did you do the working power one, going up and down steps?
I think that's the one I don't have.
Did you do the energy one last time?
Yeah, energy's the one
We had the pendulum.
No, I did the one we had the balls in here.
Okay. So working power you don't have either?
Yeah, I don't have that one.
Okay. No, you do.
All right.
Okay. So get with any one of the teams. I'd say get one of the teams that only has 2 people in it, and get the data from them. All right. Now let's see. Where were we? That's what I was doing. All right. I only wanted to do that one because I knew the water was boiling and I knew my ice was melting. I wanted to do that before it wasn't as good. All right. Now, let's pick up where we were before. Everybody except maybe Wayne, who's still getting his, has the data table 16.1 filled out, right? Okay. Now what I want you to do on going further, this is on page 151, the top part of the page. Use your data from your best trowel or your better thermometer, okay? So the one that had the least error in it, both at the melting and the boiling. So pick out one of those, either one of them, okay? And then what you want to do on that one, on your data table, what you need to do is your observed melting point, okay, and observed boiling point. What I want you to do on the best one, you don't have to do it on both of them, just the best one. I want you to calculate what that temperature was in Fahrenheit. You have degrees Celsius down there, right? You remember how to do your convert from Celsius to Fahrenheit. Okay, you're trying to get the degrees Fahrenheit.
10 times 10 times 2. 2.54 cents.
Mass calculate the delta time.
What's that?
Q equals
No, that's specific heat. That's what we did tonight. This was what we did last week. Okay? You've got degrees Celsius here. Okay? What you have to do is do a conversion. Okay, you've got degrees Celsius. You fill that in for both boiling and thing. What you're going to do is multiply this by so many degrees Fahrenheit here over so many degrees Celsius. What is that ratio that is Fahrenheit to Celsius? Remember this from last week? Dolly Parton song? 9 to 5. 9 degrees Fahrenheit for every 5 degrees Celsius, right? Okay? Get your mind off that. Okay. Okay. All right? That's going to give you degrees. What that's going to tell you is how many degrees above. You fill in either your
boiling point
or your melting point, either one there. Whichever. You're going to do them both. Multiply by 9, divide by 5, and then you got to add 32 degrees Fahrenheit because you got to get back up to the freezing point. 0 on Celsius is the same as 32 here, so you have to add to 32. That will give you your degrees Fahrenheit, both for melting point and freezing point. So you do this twice, once for melting and one for freezing. And before you proceed, let me see what those answers are, because I want to make sure you do them right. Otherwise, your graphs are going to stink.
On the 0, Dr. Fowler, it would be 32 degrees Fahrenheit.
because mine was 0.
Okay? Then you know what does this come out being? If you do the calculation?
That's 32.
Yes, it'll be 32 Fahrenheit. There you go.
32 Fahrenheit.
Okay? So that was easy.
Yeah.
Okay?
Next.
Now your next one.
That's through the boiling point.
Yeah.
Boiling point was 10, 101.
Okay. Now,
Plus 32.
213.8 degrees.
So when do I?
okay, on the same block that you have your, which one are you using?
Okay, this one was 30.
That's your best. 32 degrees Fahrenheit.
And then that one was 2, what it was,
213.8.
13.8.
Okay.
Y'all got how to do it? You got how to do it?
No, I'm lost.
What you do is that answer right there be 32.
Oh, okay.
Just like mine.
Yeah, that's right.
But you need to put that Fahrenheit 32, 32, and then you'll do this right here.
9 times.
9, 98 times 5 divided, times 9 divided by 5 plus 32.
Oh, here it is.
Hey, good to see you.
Times 9 divided by 5 plus 32.
Okay. Lacey Lindsay's here. Okay.
So you want us to do both of them?
What?
You want us to do, or you just want us to do,
You're better.
yeah, so I did these two, right? You don't want me to do these two?
No, just the
Okay,
best.
just, okay,
Okay.
all right.
All right.
I did it wrong. I did it first. Of course. Okay.
So you don't have to, you just want you to do two of them, you want one of them.
Yeah.
You wanted the better one.
Do the better.
Oh, okay.
Okay.
Times 9 divided by 5 plus 32.
212.
No, it's 212.3. It's 212.3 degrees.
Not on this
Okay. Have all of you made your conversion?
Yes.
You've all converted, right? I won't ask you which. I won't ask you what religion. No, I'm just kidding. Okay. Okay.
The long roll, the wrong roll. That's another one. You like them? I like the mints. Got the favorite one. I like the mints. I don't like the mints.
So that's what we got.
Okay.
So it's at 9 per 5 degrees Celsius. 9 per 5.
Huh?
9.
Yeah, 9 degrees Fahrenheit for every 5 degrees Celsius. Okay. Yeah. Now, everybody got their conversions done. Okay. Now, what we'll do next, if you go to, it says use on page 151, going further. Using the data from your best trial, okay, make a graph by plotting Celsius temperature scale on the horizontal axis and Fahrenheit temperature scale on the vertical axis. Calculate, okay. So, here's what I suggest that you do. You don't have to do it this way, but this I think will work fairly well. Okay? If you make this one over here, negative 20 on the horizontal, 0, 20, 40, 60, 80, 100, 120. That gives you spare on both ends. Okay, negative 20 on the end, then this is on the horizontal part. 0, 20, 40, 60, 80, 100, and 120. Okay? That's on the horizontal part. You really don't need the minus 20, but you got room, so I'll not put it in. Okay. Now the Fahrenheit gets a little tougher. Okay? And what I suggest you do is 30 down here. This is on the vertical scale. 30, 50, 70, 90, 110, 130, 150, 170, 190, 210. Okay? Your darker lines, starting with 30 at the bottom, then go up by 20. That would be 50, 70, 90, 110, 130, 150, 170, 190, 210.
They said 36 to go up by 30.
Okay, yeah, going up. Now wait. Turn it the other way. Turn it this way. No. Like this. Okay? Now down here, this is negative 20 here. Okay? This is 0. 20, 40, 60, 80, 100, 120. Okay. And this is 30 down here at the bottom. 50.
Yeah, that's right. 190.
50, 70, 90, 110. It's hard to see, but it's 30. 130,
70. Here's the line. Here's the line.
70, 90, 210. I I guarantee you, every one of you are going to have to do a few more blocks at the top in the upper right corner, but I'll let you figure out that in just a bit. Okay? Now, you've got just 2 points. One of them is, on your Celsius, is this your best one? 0, 32. So 0 on Celsius, this is Celsius down here. Degrees Celsius, right? And this is Fahrenheit here. Okay? So you have 0, 32. You have 2 above the baseline. Yeah, over here, right there. Okay? And then the other one is 101 and 213. That makes it 214. Okay. Well, 102, what was 102 or 101? 101. 101. Okay. One past 100. Right there. And if you go up here, well, that only goes to 210. So, no, you're fine here. Yeah, you're going to have to go up some. Yeah. And you have to just make you a few more blocks. That'd be 13. 1 more would be 14. Okay, yeah, but you go over 1.
Oh.
Yeah, because you're 101. Okay?
We rounded up to 14, didn't we?
Yeah. Okay, everybody see what you're doing on your graph. You only have 2 points, the freezing point and the boiling point.
I don't know why I did.
You're only going to do that here. Oh, this one's going to be down here, this one's going to be down here, so that's where you're going to do your extra.
Oh, over here. Okay.
Okay. Y'all can work among yourselves and help each other out, all that kind of stuff.
I'm not gonna have to. Do you want me to make the blocks all the way open?
No,
That's gonna be it
you're
right
only going
there.
to be, in fact, you only needed one set of them right there.
Oh, okay.
Right there.
Okay. I guess I felt like drawing.
That's fine. Okay? Now you draw the best straight line you can between this point and that point. Okay. Now you calculate the slope of that line. And that's actually pretty easy. Oh, don't give me that. Remember what slope is? Change in vertical over change in horizontal. Guess what?
0, 0.
Guess what? You go right back here. There's your change in vertical. Oh, so yeah, the difference in these two. There's your change in horizontal. The difference in those two.
So I need to write that on the question?
Wherever you want to write it. Okay? The question we're on going further, what is the value of the slope? You can fill it in there if you want to.
Okay. It was the meaning of, so I need to write
Okay,
the
you'll
meaning.
need to write that after you figure out the value.
Okay.
Sorry, I don't know why.
Okay, y'all just doing okay? Any questions? If you have questions, please ask. Don't be doing something wrong.
Okay. Okay.
We're doing vertical. Our vertical would be 0 to 98. Our vertical is from here, and our horizontal is from here.
Which is the best?
This one.
That was the best. Okay. Well then, okay, you calculate Well, whichever of these two is the best. Okay, then do both of those on the same. Okay, whichever. You choose. Okay. Well, if you got that one calculated already, which it looks like you did, then the change of vertical is this minus that. Change of horizontal is that minus that. Are there any other questions? I'm just going to pause this just to keep from burning so much tape.
You said for the value of the slope,
Right.
use
Okay.
these
Difference in those two.
two. And these two.
This one minus that. That's
Okay.
your rise.
Do I put the 0.8?
Yeah, whatever you want.
We just put 214 like we rounded.
Whichever you want.
Okay, 214 minus 32. Okay.
Okay, that's your numerator. And your denominator is the difference in those two.
So we subtract these two from each other.
Right.
And then add them,
No, that's your denominator. Subtract this minus that.
which is 101.
101, so that's in your denominator.
Mm-hmm.
So you put that under the 214.
Oh, make it a fraction.
Make it a fraction.
Gotcha. Okay.
And then on the calculator, the top divided by the bottom.
Bottom.
Yeah.
Gotcha.
See what you get.
Okay. You got, come on, Philip. Work it out.
What's that?
I said, I told Philip to come on, we'll work it out.
Okay.
So this is what you said
Yeah.
just for the top,
I'm sorry.
the bottom.
Okay, what's the question?
What was you saying using for the bottom?
Okay. Have you done your conversions to Fahrenheit? Okay. I would put those on the table over here. Okay.
What's that?
Okay. Which was your better one? Trial one or trial two? Trial two. Okay. Put the Fahrenheit reading here. I know you know that one. Okay, and then your Celsius there. Okay. Now, the difference between these two is your rise. Difference between those two is the run. So it's rise over run. So the difference of those two. Is that what you've done already? Yeah.
The meaning of the slope is the
Right. And then divide that.
Subtract these two from each other.
Then you divide.
So this
Yeah,
number,
that's
this number.
what
So
fraction is.
Fahrenheit,
Divide.
subtract
Numerator
it.
divided by the denominator.
Okay, cool. Then you subtract
See what you
this
get.
from,
And I did that.
that's 98, and then you divide the denominator into the numerator, and that gives you your answer.
What did you get?
0.55.
No, you didn't. Let me watch you do that on the calculator.
I did.
Let me watch you do that on the
Okay.
calculator.
The man right there did how.
Okay. Wait. That's not what you said.
1.8.
Okay.
No, mine is 101.
No, wait. What is divided by what?
Be right there.
The denominator is divided by the.
No, numerator divided by the denominator.
So 182 divided by 101.
That will give it to you.
1.8.
Very good. You write that on the, where is it? I had that. Oh, here it is. Okay. You write that.
And that's
Here.
the barometric.
It says what? No. What is the value of the slope? What did you get?
1.8.
Okay, good.
I got 1.80.
All right, very good. You write that here. What is the value of the slope?
1.80.
Okay.
And then I got to write the meaning.
I'm on the wrong one.
Right. And then it says, what is the meaning of that?
Mm-hmm.
Okay. Now, if you needed units for that, what was in your numerator?
What was 181
No, yeah, but what was the units of the thing in the
Centimeter.
numerator?
Fahrenheit.
Degrees Fahrenheit
uh-huh.
divided by degrees Celsius. So those would be the units for that 1.8, be degrees Fahrenheit per degree Celsius.
Degrees Fahrenheit.
Per over degrees Celsius. Okay? Now that should give you a hint.
That's for this right here.
Yeah.
The second half.
What is the meaning of that? That's how many Fahrenheit degrees for every Celsius degree.
So that means we need to do these. You said these two right here. Then you said something about these two.
No, I said your units. This was in your numerator, that was in your denominator. So you had degrees Fahrenheit per degree Celsius. So that's what the meaning is how many Fahrenheit degrees for each degree Celsius.
Oh.
Okay? Now, I want you to do something for me. That ratio you see on the board that says degree Fahrenheit to degree Celsius, you see that? Dolly Parton?
Do that again.
Do that on your calculator.
With that.
With the 1.80.
No, do that. You see the degree Celsius, Fahrenheit per degree Celsius?
It's blank.
No.
Oh, I got you, 1.8.
No. Okay.
This which one? This
Don't you see a
1.8?
ratio? Right there.
9
9
times
divided by
divided
5. Yeah, divided by 5. What do you get?
I get 1.8.
Oh,
What
wow.
is it?
1.8.
Oh, the same thing we got.
Yes, that's the meaning of it. It's how many degrees Fahrenheit for each degree
You broke
Celsius.
me down for all that.
Yes.
I'm ready to cry. Pull my hair out.
Okay.
I know,
All
right?
we had to do
On the
was-
sides, didn't you? Okay.
How many degrees Fahrenheit?
Okay, yeah. Okay, now the y-intercept, remember you moved the y-axis over
Degrees
one block,
Fahrenheit.
remember?
You said how many degrees Fahrenheit?
Height per each degree Celsius.
Yeah, for self.
Per degree Celsius.
For 2 degrees.
That's your supposed to write
That's what I got.
That's okay.
0 degrees Fahrenheit.
Okay, now your y-intercept, y-intercept, you that one right there.
I see.
What
I
was
didn't
that?
see that. I was like, I'm looking for a sentence.
It goes like that's 0 degrees Fahrenheit. 1.8.
Y-intercept. That was, it should be 32. You put 31.
What is the value of y-intercept?
Oh, yeah, you're going up. You're right. That is 32. So there's the y-intercept, 32.
What's the value of the y-intercept?
Yeah, the y-intercept, now remember on your graph, turn to your graph. Oh, you have it, okay.
I don't know what it's like.
Okay.
The value of the Y.
You had it upside down, but it's fine. Yeah. Okay. Okay, wait. What you were supposed to plot here was, which would you better try? Can you tell me? But no. Last time you told me it was this one.
It is this one.
Okay, you need to do that conversion. Right. You need to do the conversion, or you need to get it Fahrenheit for that.
Oh. I thought we could choose.
He wanted you to.
Y'all need to fight it out and tell me, okay?
I chose,
Now, what's your question?
Okay, number 3. You want us to go ahead and work that?
Okay. Number 3, on the going further, page 151. The slope-intercept form for the equation of a line is y is equal to mx plus b. Y'all know that one? Call it the slope-intercept form, right? Where y is the variable on the vertical axis, y-axis, in this case, degrees Fahrenheit. X is the variable on the horizontal axis, in this case, degrees Celsius. M is the slope. You calculated the number 1 above. B is the y-intercept. You recorded in number 2 above. Okay? Use that information to write the equation. That's M. Okay, mx. This is mx plus b. M. Okay, that's M.
Okay,
This is M right there. The
Okay.
slope is M. Right.
Okay.
Okay.
And then it'll be plus B.
Okay, and B is the
That's
y-intercept.
right.
You got
Okay.
that. Okay. Use this information to write the equation of the Celsius Fahrenheit temperature graph. So what would that be? What did it say the y was?
Y 30, 32.
No, the y.
Y intercept.
No, what does it say right here?
Oh,
In this case,
Y is the intercept.
what is the y? Variable on the y-axis, in this case.
Is B.
In this case.
F.
In this case.
Yeah.
Degrees Fahrenheit.
Oh, okay.
So that's
okay.
what you put instead of the y. So put degrees Fahrenheit. Okay.
Make that small.
okay, is equal to
1.80.
1.8.
1.8, okay, times, that was your slope. Your x, no, what did it say the x was? In this case,
C.
degrees Celsius.
Which is 32.
Degrees Celsius, no, degrees
No,
Celsius.
Celsius.
That is your x,
Oh,
degrees
okay.
Celsius,
Mhm.
okay?
Mhm.
Plus, your b is the y-intercept,
32.
32 degrees Fahrenheit. Okay?
Okay.
Now, wait.
Okay.
You've written that,
Mhm.
okay? What is the meaning of that equation?
The meaning would be to take convert Celsius.
That
to
is
Fahrenheit.
exactly it. It's your conversion from Fahrenheit to Celsius. Celsius to Fahrenheit. Yeah, because that's the same equation I wrote up there, isn't it? Except I
Yeah,
said
that's
9
what-
to 5,
9 to 5, but-
9.8. It's
Okay.
exactly the same equation. It's your
But you just take
conversion.
the 9 to 5 out.
No, the 9 to 5 is 1.8. Remember, you calculated that.
Okay.
So that is,
Yeah, we divided
yeah,
it, we got
and that is
1.8.
your Celsius to Fahrenheit conversion formula. Exactly. Okay? Okay. All right. Now, is everybody on the same page pretty much? Okay? Those who came in late, have you gotten the data from table 16.1? Right? Okay? Now, in addition to what you did in the data table, you also needed to pick your best trowel, the better of the two trowels, and calculate degrees Fahrenheit from this formula here. You've done that too? Everybody? Everybody's listening? Okay, I hope so. All right. So once you've got that, then you turn back to going further, and you do your graph of these data, the best of data, on your graph. Everybody's done that, right? Once you got that done, then you do your calculations here. What's the value of the slope? What's the meaning of the slope? What's the value of the y-intercept? And then, number 3, that question there. Okay? Now, when you've done all that, you've done most of what the data called for. Now, we did a invitation to inquiry. Now, you don't have to do in terms of Charles Ball Boyle's law because we haven't talked about that, but maybe from the molecular point of view you did. Because in the hot can, the molecules are very hot, they were steam, and they were very far apart. And when you inverted that in the ice water, suddenly they got much cooler, they got closer together, and they condensed, getting much smaller. And because they're much smaller, then the pressure inside the can was much less than the pressure outside. Atmospheric pressure compressed that can. That's what did it. Okay? And that's all you have to do is number 1 there. Okay? Now, then go back, and don't forget to do this, folks. Go back to your results on page 149. Okay? Now, you have to think back about what we were doing. Did the temperature change while the ice was melting? And that first thing, once you got your the thermometer into the water there, and it came down to its temperature, did it change any further?
No.
No. Even though the ice was melting, right? Okay, what we're going to find out next on Tuesday is when you have a change of phase, which is what we had, ice to water, solid to liquid, you don't change temperature. So that's exactly what you got there.
So number 1 is no, it did not change.
Yeah, well, yeah, from what you observed, okay? And offer an explanation, I think I just did. Okay? Huh?
Can you say that again?
Okay? Did the temperature change while the ice was melting?
No.
Okay. And offer an explanation for that. Because that was a change of phase, not a change of, not specific heat, but we'll get to it next week. It's a change of phase. And if you
No,
change of
because it
phase,
wasn't
you do not
changed.
have a change of temperature.
You said no because that was a change of phase.
And at a change of phase, you don't change temperature. That's enough. Next week we'll know it better. Thursday we'll know it better. Okay. Number 2, we talked about at the very beginning. So if you weren't here, either get with someone who was or listen to Screencast-O-Matic when it gets uploaded. To talk about how the atmospheric pressure affects the boiling point of water. Now, why do you think that would be the case? If you have a higher atmospheric pressure, that means the atmosphere is pushing down on the surface of the water more than at a lower atmospheric pressure, right? So if the water is trying to boil, at a higher atmospheric pressure, you got to get to a higher temperature to overcome that force, to overcome that difference. If it's like we had at a lower atmospheric pressure, it means there's less weight on the top of the water, so it boils faster. It's easier at a lower temperature. Okay? The front part of your lab talks a little bit about that too. Now, account for any differences observed in the melting and boiling point readings. Okay? You did 2 different measurements, and you knew what was accepted. Some of them were right on the money, but some of them weren't. That's what it says, account for differences. What do you think the differences might be?
In number-wise, that's what you mean?
Right, you can talk about the number-wise, but why would you have those? Let me give you a hint. These are old thermometers. Well, no, they may have gone out of calibration.
The reason why his didn't work at first.
Okay. May have gone out of calibration. You know how you have to calibrate equipment periodically?
Oh, yeah.
Well, how do you calibrate a thermometer? Once you got those marks on there, it's hard to change it. So there may be a little bit of calibration. Okay? Now, number 4, how would the temperature differences determined in this investigation influence an experiment concerning temperature if the errors were not considered? Yeah. What's that? Sorry? Oh, have you just gotten here?
She's been here. But
Did
she
you
went
get
out.
what?
She went out. She didn't before.
Oh, I didn't know that. Why didn't you say something? That's plenty up here.
Don't back up too quick.
Okay?
Number 4.
And number 4, I think it's pretty straightforward. Oh yeah. How would the differences determined in this investigation influence an experiment concerning temperature if the errors were not considered?
If the errors.
Right. You notice, remember on your data page, that's page 152, you put your measurement error. Some of those were 0, but some of them weren't. Right?
Yeah, mine's
Well,
was.
yeah, and if you didn't take that into account and use the reading that you got, you would be off 1 or 2 degrees or whatever, right? You wouldn't have a true reading. It's a very good way of saying it. Okay? And then I'll let you answer number 5 however you feel like you should answer it. Okay? Okay, help one another out.
I'm gonna elaborate. Wear out. Mine's right. I may elaborate.
Let me put these temperature things back over here.
What's that? Yeah, put them in the. Thank you.
You're welcome. I'll give you our rulers back too.
Yeah.
And at the moment, you want to start taking them out.
Oh, yes. Thomas, say the word.
That's what allowed me to come.
Converted to Fahrenheit, so Celsius to Fahrenheit. Figure out the tolerances.
It's fine.
Error, percent error.
Yeah, that's fine. Perfect. Thank you.
Percent error in testing.
That's
Appreciate
extra,
it.
that's extra points right there.
Oh, yeah. Wipe it off. Okay.
You want me to pull that ice out too, like that bucket?
Yeah, okay. Don't touch anything that you might be hot.
Oh,
Let
I
me
already
check
poured the
that.
hot water.
Oh, you did? It was okay. Yeah. The ice can be done. I'll pour it. I'll be
That's what I wrote. I don't think you see legitimate these companies.
They would gain an extra ruler somehow, but thank you very much.
It might have been mine, I think I left
What's
mine.
that?
I think it's mine, I left mine out.
Oh, you have one? You remember what color it was?
He says blue. There it is.
Yeah, it's
Several
one
blues.
of
I'll
mine.
let you- I'll let you
You're
choose.
right, Lou.
For 18 cents.
That's where I got it out of this.
Yeah. 18 cents. It was on sale. Oh, good.
Okay, does anyone need the formulas and equations from the board?
Please don't erase them yet,
You gonna
Doctor.
give us back
Okay.
our land? I'll just.
Please.
No problem.
Bear with me.
Okay. Does anyone have any more lab equipment out?
Yeah.
Okay. I'm going to haul these down to the lab. Just so.
You need a hand with that?
No, I got it.
You sure? I'm gonna set my lab.
Oh,
there,
okay.
the lab one.
Oh, the last one. Put it on the grade book. Thank you. Appreciate it. I'll be right back, folks. Y'all need me sooner? No, okay, I'll be right back.
That's why I didn't do the audio. Do you really?
Y'all still busy working? All right, good deal. Thank you. Good with that one too. Good deal. What's that?
Taking the test over there.
Yeah,
We'll
yeah.
go and walk over there.
yeah, sure. Have you finished your lab or?
Yeah, we'll turn all the ones I had missed. I'm just gonna turn them to you one time.
Okay.
I'm gonna send this over and take a break.
Okay, sounds good. Thank you.
We're just gonna meet you in the classroom.
What's that?
We're gonna meet you in the
Yeah,
classroom.
yeah, we'll go back to the classroom.
We're gonna take a little break.
And,
We'll meet you.
Okay,
This is from last week.
okay.
Somebody gave me the thing, so.
Thank you. Oh my.